In this lecture, I'm going to walk you through chapter 16 of the textbook, Multinomial Processing Trees. And as you know by now, the textbook is available online, so you can read it for free. The source code for the textbook is also available, and if you want to buy the physical version of this book, you can do that too. And ideally, I think you should read chapter 16 as well after watching this lecture. That would help you understand a lot of the details much better. So basically, the plan today is that I'm going to introduce the idea of multiple categorical responses instead of binary responses of the type that we have in in question response accuracies and things like that. And that kind of likelihood function, so the multinomial likelihood, can be then used to investigate situations where you have more than two responses, and this can be a very useful tool for modeling different kinds of phenomena, as I will show you. So I will give you an example of modeling picture naming abilities in aphasia using multinomial processing tree models. And then eventually we will take a look at a hierarchical version of the multinomial processing tree model. Okay, so let's get started. Multinomial processing trees are a very well-known modeling tool in mathematical psychology. So there's nothing new there, but what is interesting and new, arguably, I guess, is that the STAN probabilistic programming language allows us a lot of flexibility in building these kinds of models with a hierarchical structure, right? So that's where that's the main point, of this lecture, to demonstrate the power of the STAN language in elaborating such a model. So as an example, we look at a word production task, right? So where you might have individuals with aphasia, right? So this is a language impairment disorder that's due to some kind of cerebrovascular accident or head trauma, a stroke, for example, right? So, so the word production task is the following: the participant has to name the object that they see in a picture, usually on a screen. So, for example, they might be shown the picture of a cat, and what they have to do is they have to name the animal, right? The picture, the animal depicted in the picture. So what could happen? Okay, so you could get a bunch of possible responses. One could be that they could, one possible response could be that they give the correct response and say cat. Another possibility is that they say a word, and this happens with individuals with aphasia, that they end up saying a word that is semantically and phonologically related, like rat, when they actually intended to say cat. Okay? Another possibility is that you produce some semantically unrelated but phonologically related word like hat or something, right? And finally, it's also possible that the participant ends up producing a non-word. Okay, so these are all possible responses, and these are multinomial responses now, right? So there's more than two possibilities. So the interesting thing here is that the researcher might have a theory about how each of these responses comes about. And the assumption is that there could be some probabilistic events that lead to the participant producing, one or the other response. So that's a theoretical process model now, right? And so what we are going to do is eventually in this lecture is what we're going to do is we are going to implement such a process model, right? So this takes us far beyond standard data analysis where you just compute estimates of the probabilities of producing this or that response. You're actually modeling the underlying latent, processes that you can't actually directly observe, but you have a theory about. Okay, so you will see some examples of this, of course. So before we get into multinomial processing tree models, what we need to understand is how one can model multiple categorical responses, right? So a standard, binomial likelihood would involve simply yes no responses or 1 0 responses or something like that. But you can also have, as I just showed you, a situation when you have more than two. So the multinomial distribution is a generalization of the binomial distribution for more than two possible responses, right? So let's take a look at how this would work. So let me first remind you how the binomial likelihood works, right? So if you think about the binomial distribution, I assume that you are familiar with the DPQR family of functions, or that you remember them from chapter 1 of the textbook. And so one of the functions we learned in chapter 1 was this R binom function that generates random data from a binomial distribution. So you could have um, one experiment with 10 trials, right? And a probability of success could be set to be 0.5 to generate some random data. And then if I were to run this over and over again, I get different numbers here ranging from 0 to 10. Of course, because the probability is set at 0.5, the most likely values will be near, the most frequently occurring values will be near 5. Okay. All right. So we can also, instead of doing just one experiment with the R binom function, we could do multiple experiments. And then what you would get, each experiment has size 10, right? Probability of success in each of the 5 experiments is 0.5. So what you could get is a sequence of, numbers of successes, right? So this is just one experiment. This is 5 experiments outcomes here. So that's how we use the R binom function to generate simulated data, right? Now suppose that we have 3 possible answers, not just 2. So we would then assume that each of those possible answers, so for example, assume that we have yes, no, and don't know as the possible responses. So we could assume that each of these possible responses has some probability of being produced, right? So of course these 3 probabilities has to sum up to 1, right? So I've just chosen some arbitrary numbers here for the 3 different possible responses, right? So the just like the R binom function, there's the R multinom function that you can use to carry out a single experiment with 10 trials. And what you would get as and of course you provide the 3 probabilities that I just specified. And so if I just generate some random data with this, what you would get is a column vector, right, containing the number of instances produced of each of those 10 trials from in each of those 10 trials. So this sums up to 10 because the number of trials here is 10, right? So what we have in this particular generation of random data is 1 instance of yes response, 2 instances of a no response, and 7 instances of don't know response, which basically is in conformance, with the probabilities that we set up. If we had set up the probabilities differently, like if we had set 0.8 here for the yes responses and 0.1 here, then the most frequent response would have been a yes response. Okay, so that's how you would generate simulated data in this kind of setting. Okay, so now, just like the binomial case I just showed you, you could carry out 5 experiments, right? And each of size 10, so 10 trials in each of the 5 experiments, and then the same probabilities again. So this time what you would get is for the 5 experiments, right? Each of them you would get some randomly generated number of correct responses for each of the 3 categories. So this is yes, this is no, this is don't know, right? I know that because that's the order in which those probabilities are defined in the multinom R multinom function. Okay. So now this is the multinomial distribution that we're talking about, but there's also a sister distribution to that one, which is the categorical distribution. And this is the generalization of the Bernoulli distribution. So if you remember, the binomial distribution and the Bernoulli distribution are tightly related to each other, because the binomial distribution assumes that you have one or more trials, but the Bernoulli distribution assumes that you have only one trial. Okay, so they're basically the same thing, but it's just that the number of trials will differ. And so the multinomial and categorical distributions are also analogous in that sense, right? So as I will show you. So if you remember, like in the Bernoulli distribution, you can generate you can carry out 5 experiments, each consisting of one trial. Okay, so in the Bernoulli, we don't define size, just like as we did in the binomial. Remember, in the binomial, I defined size, which is the number of trials that I have. In the Bernoulli, the number of trials is by definition 1, right? That's why it's a Bernoulli. So therefore, when I use a Bernoulli, I don't define size at all, right? And I mean, in fact, there's not even a parameter for that in the Bernoulli distribution, right? So there shouldn't be. I hope that there isn't. Anyway, so like so I'm doing 5 experiments here, each with probability of success 0.5. And so what I'm going to get this time is, because the number of trials is by definition 1, I'm going to get a 1 or a 0, right? So I got a 1 here and a 0, 4 zeros after that. This is kind of a surprising result, by the way, as a simulated data set, because there's a 50% probability of success. So I got some pretty wild data here. So that's interesting. And so I could do the same, I could generate the same type of data in using the R binom function. Again, doing 5 experiments, but each of size 1. So these 2 commands are exactly identical, okay? And again, I get a surprising result each time I got success, right? Which I shouldn't have had. But that's the nature of randomness, right? There will be a lot of variability when you're simulating data. All right, so basically you have the Bernoulli and the binomial. Bernoulli is one trial, binomial is usually used for more than one trial, but you can use it for one trial as well, of course. And then similarly, you have the categorical, which is for one trial, and the multinomial, which is for one or more trials. Okay, so the rcat function in the extra distr package, so you would have to install this package to get this function, and then load it before you run the rcat function. This will generate categorical data, right? So here's the command. Here I'm running just like the rban, the Bernoulli function. I'm doing 5 experiments, simulated experiments. Probability of success is given here. The labels for each of those 3 is yes, no, and don't know. And so what I get back when I run this rcat function is 5 outcomes, each consisting of one trial. And so in the first experiment, I got a don't know. The second experiment, I got a don't know. In the last experiment, I also got a don't know, which is not surprising since the probability is set at 80%. And for the others, we got a yes. Okay, this happened. Oh, yeah, we just got yes in the other 2. So that's not a surprising result, but it's an example of how you would generate simulated data here. Okay, so this is, of course, just like the binomial could be used to generate data like a Bernoulli. We could use a multinomial with size equal to 1. Here we go, size equal to 1, to generate exactly the same type of outcome. So, but the format in which the outcome will come out will be different. So again, same situation, 5 experiments, size 1. This is exactly the same scenario as the rcat distribution function here. So what's going to happen now is that these are the 3 responses: yes, no, don't know. And here are the 5 experiments, each of trial 1. So what you're getting in each of the experiments is a sequence of zeros and ones. And what this tells you is that in the first trial, the first experiment, you got don't know. Second experiment, you got a don't know. Oh, in all 5 experiments we got a don't know. Okay, so that's just another weird random outcome. So we should have had it. I mean, if we ran many more of these, what would happen? Let's say if we ran like I don't know. Let's just do it. If I ran 100, you know, instances, 100 experiments, you can just see that we will eventually get some. Um, we would eventually get some cases of what's happening here. So let's say I run 100 experiments, each of size 1, and what would happen is maybe if I want to do column sums, if I do column sums, I should be able to find no, row sums is what I want, right? Let me see if I can do this. Trying to do this on the fly is never a good idea. So row sums, right? So what I should get is 14 instances out of 100 for yes, 5 for no, and 81 for don't know, which is roughly what you would expect. I mean, if I ran it again, I would get different numbers, you know, each time. So this is just random generation of data. And if I increase the number of experiments to some larger number, let's do this, okay? So let's make it like 100,000 or something like that. So now we have a lot of data coming in. So what would now happen is that we would get closer and closer to the probabilities, you know, that we have set out here. So, right? So it's of course a function of the amount of data that you have, that you would get closer to the true values that are supposed to be producing these data. So with just five experiments, you're going to get a lot of wild variation, like in this case. Okay. So anyway, what I've illustrated now is the R multinom function, the R cat function, and the relationship between them. It's just like the relationship between the R binom and the R Baron function, right? Except that we have multiple responses, more than 2. And by the way, I could have added even more possibilities, right? So I could have had 4 possible responses or 5 possible responses. So all that would change is the number of rows that are coming out in this R multinom output, right? So I'm not limited to 3 possible responses or anything, right? All right, so let's now consider a situation where we are going to generate some simulated data using the multinomial distribution. Okay, so we are now going to actually try to create some simulated data for the problem that I discussed earlier. So aphasia, we have a picture naming task, and as we know, individuals with aphasia have difficulty naming objects, you know, that they're shown. So that's what we're going to simulate, right? This is actually this kind of test is administered to suspected patients, patients who are suspected to have aphasia, in order to evaluate them, you know. So these kinds of tasks are pretty common. Okay, so here are the possible responses that we'll set up. So as I said, instead of 3, we have more than 3 now. So we're going to say either the response will be correct. So for example, the participant is shown cat and they name it correctly, or it'll be a neologism. I hope I'm pronouncing that word correctly. CAG, so like a non-word, right? But phonologically it's related to cat. And then you could have a word that is only phonologically related to the target word cat, like hat, right? But not, it doesn't actually match the word in meaning or anything like that. A mixed possibility could be that it's semantically and phonologically related, right? So rat is related to cat, but it's not, and it's phonologically close, you know, there's just a minimal pair there, but it's obviously not the correct answer. And then of course you can have situations where, you know, individuals with aphasia are often slower than unimpaired controls. So if there's a timeout in the picture naming task, then you may have no response, or the participant may just blank out and just can't give a response, right? So there might be a no, non-response as well. Okay, so all kinds of things can happen that would be falling into this category. Okay, so let's generate some data, right? So let's take a look. So first we'll do the following. We will define the true theta probability. So remember what we're doing is we are generating simulated data here, okay? So to do that, we have to decide on some probabilities for each of the possible responses. So here are the 5 possible responses, and we just set up some arbitrary probabilities. These probabilities have to sum up to 1, by the way, right? So what we've done here is that we define the probabilities for the first 4, okay? And then for the last one, we chose a probability that we defined the probability to be 1 minus all the sum of all the others, right? That's why you got this long and complicated output here to define the theta correct. And that's because we want to make sure that these 5 probabilities sum up to 1. And so we can check that, right? They should sum up to 1. So that's important, right? Okay, so what we have now is this true theta vector that contains the true probabilities, and we're going to use that to generate simulated data from a multinomial. And we're going to run an experiment with 100 trials, right? So one experiment with 100 trials. So size is equal to 100 here because 100 is defined here. So in just like in all other functions in R, you can drop the name of the parameter. So instead of writing size equal to n underscore trials, you can just write n underscore trials as long as you respect the order in which the parameters are defined, right? I hope that's clear to everyone. That's why I didn't write size here. It just gets very verbose and hard to read if we keep writing the names of the parameters, right? So we got one experiment, 100 trials, and a vector of true theta values, okay, which sum up to 1. And so if we run this and save it as answers from a multinomial, this object is a column vector, okay? And this contains the number of instances out of 100 that belong to each of these 5 categories. So this should sum up to 100, okay? If it doesn't sum up to 100, there's something wrong, obviously, right? So what we are now going to try to do is we're going to define a model that, let's say this is our actual data, okay? Suppose we've simulated some data. This can be treated as observed data from a real experiment. And so that column vector here, right, of these responses will be modeled as a multinomial with a multinomial likelihood with some true theta values, which we defined earlier. Okay, so theta is those 5 values that I defined earlier. So now, of course, because we are Bayesians, we're going to have to define a prior on the theta vector. And a common prior that is used for this kind of situation is the Dirichlet prior, okay, which is a generalization which extends the beta distribution, which you must have encountered in the beta binomial case, right? The simple beta binomial case. I discussed that in chapter 2 of the textbook. Okay, in case you haven't seen that, you can take a look at that there, right? So this is just a generalization or extension of that. So the Dirichlet prior, and this is the prior on the vector of probabilities, okay? So that's our prior, okay? And this parameter alpha in the Dirichlet prior is called a concentration parameter, and it's going to be a vector with the same length as the number of, probability values that we have. So in this case, 5. And so here what we are doing is we are setting the concentration parameter to have values 2, 2, 2, 2, 2. And that's analogous to having a beta distribution, with parameters 2 and 2, right? So just to remind you, what happens, like, let's just do it, just to generate generate the beta distribution. Okay, so I'm just going to create a vector. Let's call it x. Let's just call it x, which is the sequence going from 0 to 1 by some small number, right? By 0.01. Okay. Oh, what did I do wrong now? Oh, I put a period there. My site is not that great. Okay, so that's my x, right? So this is a range of possible values for probabilities between 0 and 1. I'm going to show you what the beta distribution with parameters 2 and 2 looks like. Okay, so I'm just going to plot d beta, right, with the data as provided here, these different values. And what are the parameters? So shape 1 and 2 are the two, alpha and beta parameters that we use in the beta distribution. So if I set the values to be 2, so this is analogous to the Dirichlet now, right? And so this is my, I'm going to be plotting this. So I want to plot this as a line because this is a continuous distribution. So if I plot this distribution, what it looks like is this. Okay, that's a beta 2 prior. Okay, so it's basically downweighting the extreme values 0 and 1 and spreading the probability mass widely around 50%, 0.5. Why is this index here? Sorry, I don't know what I've got. Why do I have a 0 to 100 here? I should have had 0 to 1. Did I do something wrong? I don't know. Something's odd about this. But but it doesn't matter. Okay, so this is supposed to range from 0 to 1, not 0 to 100. I don't know why it's showing the indices. Oh, I see. Sorry, I should have done it like this. I made a mistake. So I should have put x here and that here. Yeah, that's correct now. Sorry about that. Right. So the range, the support, the support of the beta distribution is 0 to 1. And beta 2 distribution will basically regularize, the probability, the prior on the probability parameter, assuming there's only one probability parameter, such that extreme values are downweighted. So that's a regularizing prior, which allows a lot of variability, right? If we had set shape to 1 and 1 in the beta, we would end up with a uniform prior, right? That would be a uniform prior. If I change the shape to half and half, I would end up with a horseshoe prior, like upweighting the extreme values and downweighting the intermediate values, right? So all these are possibilities. And of course, if I increased the beta parameter to, I don't know, let's say 100 or 100, right? Then I would be concentrating the prior around 0.5, very tight prior. Okay, I would never use such a prior in a normal setting unless I had really dramatic amounts of information or something, right? So prior information. Anyway, so I just wanted to show you that the beta 2 prior, its analog in the Dirichlet case is this one here, right? Okay, so the standard model that we are going to define to model this simulated data is the following. Okay, so as you know, a standard model consists of different blocks. So there's a data block which is demarcated by curly braces, then a parameters block, same property, in the model block, and then the generated quantities block is generally used to generate posterior predictive data or prior predictive data or whatever, right? So the setup here is that we have in the data block, we're going to define the number of trials, which I think was 100 in the example. The lower bound is 1. And the responses will be modeled, will be saved in the data object. Data block will be defined in the data block as an array of length 5 because there are 5 possible responses. And the values in that array can range from 0 to 100, which makes sense, right? So that's our, this is the actual observed data or simulated data in our case, and the number of trials is defined. So this will be the data that we define, for modeling a multinomial, data generated from a multinomial likelihood. The parameters are, of course, the theta distribution, the vector of theta distribution. So notice that there's this simplex here. So this says that the theta parameters are a vector of 5 elements, right? Is a vector of 5 elements, and the simplex defines ensures that the probabilities will sum up to 1. Okay, that's the constraint that is imposed by the simplex thing here. Then we define the model. So the model is pretty straightforward now. It's incredibly simple, right? So we are just saying, so I don't know if you're familiar with this target syntax, but the target syntax is actually just a variant on this statement. So when I say multinomial log of the probability mass function and answer vertical bar theta, what I'm really saying is this. I'm really saying this. I'm saying that the responses are being generated from a multinomial with probabilities theta. Okay, that's what this command is actually saying. So this you would only understand what this command does if you read the Stan manual or you read our textbook where we explain all this right in detail. Similarly, for the theta prior, we are going to, for the theta vector, right, we're going to define a Dirichlet prior, always on the log scale. Okay, so log PDF, it's a continuous distribution, and the concentration parameter is defined by a rep function, which is just like the R rep function, but it's just got a different name here. So we are generating 5 instances of 2 here. Okay, so that's those are the hyper parameters, you know, in the prior. All right, so that's the model block. That's it. I mean, the model is simple. And then the generated quantities block is what it's doing is it's generating some predicted data, posterior predictive data, right? Again, it's going to be an array with integers in it, so length of 5, right? And we are going to be generating the data from the random number generator function for the multinomial that's available in Stan. And the way we do that is by just specifying that take the posterior distribution of the theta parameters and assuming 100 trials, generate some simulated data. So this will produce a whole bunch of simulated data. Okay, you can examine that later on. If you want to run this model, you can of course run all this code. Okay, so I've provided all the code, so you can extract all the code from this chapter, or you can just work through the R markdown file and run all the commands. Okay, so I've provided this file as well. It's an RMD file. Okay, all right, so so having created this model and defined it, we now are going to create a data object which has to be a list in Stan, as you probably know. This is unlike BRMS. So BRMS does all the work for you in the background. You can give it a data frame and it's going to do all the internal processing on its own. But if you're using Stan, RStan or whatever, you're going to have to define the data as a list. So number of trials, 100, and the answers that we're getting from our simulated data are saved here. Okay, so remember what this ans mn was. It's this thing here, ans mn, right? There's a column vector here. Okay, all right, so you can look at the structure of this this list object. I didn't do that, but you can take a look yourself. And so from the bcogsci package, so this is a package that we have associated with the textbook, so you would have to install it. It's a bit of a pain, I guess. So let me show you how to install it. bnissen-boim bcogsci is the package. It's a GitHub archive. Oh, what happened here? Sorry, did I mess this up? Oh, I don't want bnissen-boim. Nissenbaum, right? So here's the bcogsci package, and it's on GitHub. And so the way to install it is that you just follow these instructions here, and so you will be able to get this package. And the package contains all the models pre-specified, so you can find this model inside the bcogsci package if you want to look at it, or you can print it out, of course, once you've loaded it. So we are using the system.file command to extract the stand model from the package, and then in the stand models directory, this is living in the stand models directory, and so we extract this model and we save it here, and then we plug in this model with the data that we just created as a list object into the stand function. This is in the rstand library, right? And so this gives us the results of the model, which you can look at with the print function. And what we're interested in here is the theta parameters, and we want to know if we are recovering the theta parameters accurately or not. So these are the posteriors, posterior means, the means of the posterior distributions of each of the 5 theta parameters, okay? And then the 95% credible interval, etc. You know all these details about the number of effective samples and the R-hat statistic, I assume, okay? So now what we want to know is whether we were able to recover the true, theta parameters. So we can use MCMC recover histogram, and the command for that is here. We take the fitted model. This is the fitted model as a data frame, and then run some magic here with ggplot2, and what we get is each of the posterior distributions of the 5 parameters, and the true value that we had put in our simulated data is the vertical line. And you can see that basically our model is recovering the true values of these parameters, right? Because the true values that we put in generated the data, so the posterior distribution should reflect that if the model is able to recover those parameters. So this is just a basic sanity check that I have discussed in previous chapters as well, just to make sure that the model actually meets the minimum requirement of being able to recover the parameters, right? So we do this with simulated data where we know what the true values are, right? This is just a sanity check to make sure that the model actually, in principle, would be able to recover the parameters. Okay, so now, I showed you how you could define the model using the multinomial likelihood. You can do the same thing, fit the model by assuming a categorical likelihood, right? So this is like in stand, when we are modeling 0-1 responses using the binomial likelihood, what we actually do is that we are modeling every single outcome, which is a 0-1 response, as a Bernoulli likelihood. That's what we do, right, in stand. So this is the analog for that in stand. We're going to use the categorical distribution to model each of the 0-1 responses, for each of the categories. So remember when I showed you the categorical function? Right, so if you remember, like when we are using the rcat function, right, we're gonna have only one trial each time. So in each trial we are going to have in each of the five experiments here, in each trial we're gonna have only one response, one of the 3 responses, right? So that's the kind of situation that we're going to be modeling now, okay, with the categorical likelihood. Where is it? Yeah, right. So, oops, sorry. Yeah. So now the model will look like this. Okay, there's a small change in the model. Okay, so first of all, we are going to write in our data block, we're going to define the number of observations, which is 100, I think, right? And we're going to create an array with that number of observations, and the 5 possible responses will be saved in this object, will be defined in this object here, w_ans. Okay. All right, so the parameters block doesn't change. It's the same as before. The priors don't change on the theta parameters, all the same. What does change in the model block is the definition of the um, likelihood function. And what we're going to do is we're going to use the categorical log probability mass function to model each of the n, responses as a function of the vector of theta values, and we're going to model that vector of responses as a categorical likelihood. Okay, so that's what that command is doing, and because we have to cycle through all the n observations, we wrap it inside a for loop here. Of course, there are more efficient ways to do this, but for now it's good enough, right? So that's why we have to go through every single element in the observations, right? In the first observation, you might have don't know. The second observation, you might have a yes. Third observation could be a no, etc. Right? So we are modeling those outcomes as a categorical response. Of course, in our example, we are working with five possible responses. Right? All right. So here's the number of observations, 100, and rcat is the function we're using to generate random data. So 100 random data points, and you have to take the vector, of the true theta values as a matrix and plug it into the prob function, because that's how Stan expects to see the vector of probabilities. Okay, so what we get as a result is the categorical responses, right? And we create a list object that is representing the data now with 100 observations, and this will contain the different 100 variable responses: correct, incorrect, non-response, etc., etc. Okay, so you can look at the output. Maybe it's helpful to see this, right? So you're getting 5 possible responses, which are labeled as numbers here. That's just arbitrary. You could have done this differently, but in Stan, I think I would want to label those as numbers, right? I think that's true. So anyway, so 5 would be, for example, correct, etc., right? So now we're going to fit the model. The model is defined in categorical.stan, again in the bcog-sci package. And so we extract the model from the stan models directory in the bcog-sci package, save it here, and then plug it into the stan function with the data that we just simulated. And if you look at the output, you'll get the 5 probabilities, posterior distributions of the theta parameters with their 95% credible interval, and the mean of those probabilities will be very similar to the means that we got in the multinomial distribution. So you can go and check that. 19.09, 0.25, 0.05, 0.41, very similar values. There might be slight numerical differences, instead of 0.25 you might have 0.24 or something, right? But that's just due to the fact that we have slight differences in the randomly generated data and the sampling process. Okay, so that's the first part of this lecture. In the next part, I'm going to talk about modeling picture naming abilities in aphasia with MPT models.
Recording in progress.
So to continue with this lecture now, I want to now show you how one could define a multinomial processing tree model for the aphasia question that I had discussed earlier. So let's take a look at what the model would look like. So we are going to, so this model is actually based on, is a simplified version of work that was published in this journal. So, and we're going to use simulated data to work with the model. So basically what we're going to do is we're going to assume, or let me show you the model itself, and all this text you can read later. But basically the model assumes that the participant carries out a sequence of processes that are really not observable, so they are latent processes, but we are going to be able to unpack those in the model. That's the big deal of the multinomial crossing tree model. So the basic idea is that when the participant sees a picture on the screen, they start by trying to make an attempt to retrieve uh, the lexical item that corresponds to the object that they're looking at, like cat, for example, right? So they make an attempt with some probability to do a lexical selection. So that attempt has some probability A, and therefore, if they fail to make that attempt, that's the other branching, the branch in the tree, then with probability 1 minus A, they would fail to uh, do the lexical retrieval or lexical selection, and then they would, in that case, they would give a non-response. Okay, so that's one way in which you can get a non-response. Well, actually, that's the only way here. Sorry, in this model, that's the assumption. Okay, so the non-response would come about if you just fail to do a lexical selection or lexical retrieval. Now, once you've done the lexical retrieval or lexical selection, the model assumes that, so it's explained here. Let me just go back here. Right, so if the lexical selection is made successfully, then the target word, in this case, in my example, for the running example, it was cat, is selected with some probability t, or some other word is chosen with probability 1 minus t. So that's this branch in this tree. So if you correctly select the right word, the target word, you go down this path with probability t, otherwise you go down this path with probability 1 minus t. So then what happens next is that once a word is selected, so either the correct word or some other word, either its phonological representation is selected with probability f, or some other incorrect phonological representation is selected with probability 1 minus f. So that's this branch in the tree here, right? So you'll see that regardless of whether you made the correct selection or the wrong selection, in the next level, your phonological choice for the word would be either the correct choice with probability f, or the incorrect choice with probability 1 minus f. That's when you've targeted, when you've retrieved the correct word. But even if you retrieve the incorrect word, right, if you were to correctly retrieve the phonology of the incorrect word, you would get some kind of mixed response. And so that would be also with probability f. So both of these probabilities turn up in both branches of this tree. Okay, and so if you had incorrectly retrieved the wrong word and could not get the right phonology either, so that would happen with probability 1 minus f, right? So we're going down a path. These are theoretically posited, processes or sub-processes that the researcher assumes when trying to understand how it comes about that the participant gives a correct or incorrect response, or some mixed response, and so on. So so now that the word has been selected, correct or incorrect, with correct or incorrect phonology, there can be a phonological change that occurs that leads to a formally related word that is selected with probability C, or a non-word that is selected with probability 1 minus C. So that happens in this last phase here. So this was the path whereby you had correctly retrieved the right word, like cat, and then the phonology went ori, and then once you got some slightly incorrect phonology for that word, then you end up either producing something that's formally related to the word cat, or you create some non-word, right? Similarly, if you had gone down this path and ended up, or this path, sorry, and ended up with the wrong word, and um, misgenerated the phonology, then you could either produce a formally related word or some non-word, right? So there's two different ways in which you end up with a neologism or a formal correlate, right? So these are possible answers, right? Possible responses that could be given in this model. So if you look, if let's count them. So there's one non-response, mixed response, neologism, and formal. So this occurs twice, so I won't count it twice. So that's 4 and then 5. So there are 5 possible ways in which a response could occur, but that response would occur as a result of going down different paths in in the in this multinomial processing tree. So that's the model, okay? And the model is theoretically motivated. It's based on this paper here that I mentioned earlier. Okay, so the parameters, in this model, this A parameter, T parameter, F parameter, and C parameter, right? These are the 4 parameters in this model. They have a psychological interpretation based on domain expertise, right? And so the parameter A is the probability of initiating an attempt and succeeding, right? Then the parameter T is the probability of selecting a target word over a competitor, right? So that's this one here. Then F is the probability of retrieving the correct phoneme, right? Either down this path or down this path, right? And then finally, C is the probability of a phoneme change in the target when you're creating a real word, right? So here, right, in this path or in this path, you might have a phoneme change that could lead to a slightly different word that's formally related, right? Okay, so these are the 4 parameters in this model, and they have some meanings, they have theoretical content. So what we want to do is now we want to figure out on the basis of these parameters, we are going to, if we walk down this tree, this is just a, basically it's showing you the possible outcomes that you can get, and the different ways in which you can get it. So what we can now do, so let's take the simplest case. I can compute the probability of getting a correct response in this multinomial processing tree, right? So the probability of getting a correct response, assuming independent, sequences of events, is that I would multiply this probability A with the probability T with probability F, right? So this path, the product of these 3 probabilities would give me the probability of producing a correct response. Similarly, if I want to figure out the probability of, let's take this easy one, the non-response, the probability is 1 minus A, okay? And what about the formal response, right? I would have to go down this path, this path, this path, this path, here, multiply all the probabilities out. But notice that formal appears twice, so I would have to compute this probability and add up the alternative way in which this formal outcome could be produced. So I would go down 1, 2, 3, 4, right? So that would be a product. This is one product, and this would be the other product that gives me, if I sum up those 2 sets of products, I would get the probability of producing a formally related word. Similarly for neologism, right? It would have to be a sum of 2 probabilities. So that's how we would compute the probabilities for each of the possible responses, right? So if you take this, the probability of a non-response, easy, okay? Similarly, the probability of a correct response, easy. Multiply those 3 probabilities out. The 2 complicated ones are the neologism, right? Because it would be the sum of this path plus the sum of this path. And similarly for formal, right, it would be the sum of going down one path with the summed up with the probability of going down the other path. Okay, so that's it looks complicated, but actually we are literally walking down the different paths in the trees to calculate, you know, the probabilities of different unique outcomes. Okay. Okay, so that's, oops, sorry, that's pretty straightforward, I hope. And then we get to, so we know how to calculate these probabilities now. Okay, so notice that the probabilities of all the possible outcomes has to sum up to 1, right? That has to be true. So once we know the first, the first 1, 2, 3, 4, the fifth one we can always figure out because we know the constraint that they would sum up to 1. Okay. So let's build a multinomial processing tree model. So what we're going to do is first of all generate some simulated data. Okay. So we're going to simulate some data and we're going to assume that there are 200 trials. And for now, we're going to assume no variability between subjects and between items. So later on, we can define a hierarchical version of this model. But let's just keep it simple for now. Okay. So first of all, we're going to define some functions that allow us to compute all these probabilities, right? So we can just write a function in R that takes as input the probability A and gives me back 1 minus A. Similarly, for the I could write a function for probability of correct responses as taking as input 3 values A, T, and F and returning the product of those, right? That's what the function would look like. So let's define those functions. Those are pretty straightforward now. So this one, just because all of these probabilities in principle depend on the 4 probabilities, all of these will go in as parameters in the function. But I mean, depending on which outcome you're talking about, only some of those parameters would be relevant, right? Here, these parameters would not be relevant here. So, right? So it's pretty straightforward. We're computing, for example, for the probability of correct is taking ATFC as the input, but just multiplying AT and F, okay? So those are the functions that we have defined in order to compute the probabilities of each of the possible outcomes. Now to simulate data, we're going to define some probabilities for each of the 4 parameters, right? Notice that they don't have to sum up to 1, right? So because they're like the probabilities of each of those different independent paths there, okay? So now once we've defined these 4 probabilities for generating simulated data, we can create a theta vector, right? The theta vector will contain the probabilities of those 5 responses, which we know how to compute because we just defined a function for each one of those, right? So it takes as input the theta vector will contain the probabilities of the 5 possible outcomes. So what we're going to do is again use the R multinomial and multinom likelihood, 200 trials. So there are 200 trials, 1 experiment, and what we have here is the vector of probabilities that we just computed for each of the possible outcomes, right? And so just generating some random data which is saved in the object as a column vector, right? In ANS answer. And so what we get is the number of non-responses, the number of neologisms, etc., right? So these will vary randomly as you generate different repeated data. So now we can model this process, okay, in Stan. So we're going to be fitting a model that's available already in the bcogsci package. MPT multinomial is what it's called, MNM, right? And so one important thing to notice that's coming up in a moment is that the probabilities of the different categorical responses will be defined in a new block that we haven't discussed yet, which is the transform parameters block. In the parameters block, we'll get the ATFC parameters, and the transform parameters block, we will compute all those probabilities, okay? because they are derived from the probability parameters, right? And if we don't define priors the um, for the parameters, then we're going to end up with a uniform prior by default. Okay, uniform 0 1 prior by default for each of the parameters, but we don't want that, so we're going to choose our own prior, right? Okay, so the model is the following. Okay, so for these are the same values, you know, that I just computed for the probabilities earlier. There's nothing new here. These are just, I'm just specifying the model now. The 5 possible outcomes probabilities are laid out here based on the ATFC parameters, and that's saved as a vector theta for all the 5 possible responses. This is just like the simple example with generating data with the R multinom function, right? And so we are now going to define a model which says that the data are coming from a multinomial likelihood with the vector of theta parameters, okay? And for the ATFC parameters, we're going to define a beta 2 prior, because we don't want to define a uniform 0 1 prior. It's a little bit too vague, okay? So as I said, the beta 2 prior for each of the parameters is regularizing in the sense that it downweights the extreme values. All right, so the next thing to do is to define the model. So the data block contains the number of trials as before. It contains an array of 5 possible responses, right? With possible, each of the 5 elements in the array could have numbers, integers that go from 0 to the number of trials, right? So that, because that's, if you see here, right, we're talking about these numbers here, okay? So okay, so the next step now is that, where was I? Sorry, I got lost. Yeah, here, right? So we've that's my data block, and then the parameters are of course all probabilities, so they're defined as ranging from 0 to 1, ATFC, straightforward. And in the next block, the transform parameters block, which you haven't seen before in this lecture at least, we are going to derive the probabilities of each of the possible outcomes. So those are in the vector theta. So this is a simplex, okay? That means the probabilities have to are assumed to sum up to 1. There are 5, okay? So for each of the 5 elements in this array, or in the simplex array, simplex vector, I'm not sure. I need to check the terminology. We are just, again, instead of writing the function that we wrote in R, we are simply computing those probabilities by going down the paths, you know, in the multinomial processing tree. All stuff that we've seen before, nothing new, okay? But of course, we need to know what theta 1, theta 2, theta 3, theta 4, and theta 5 refer to, so that so we've written that out here so that you don't forget, you know, what the probability corresponds to, which category it corresponds to. Then the model is straightforward. For ATFC, we define our beta 2 prior, easy. For with the multinomial log probability mass function, we are modeling the answers, right? The responses as a function of theta. And so that's it. That's the whole model. That's the multinomial processing tree model without any hierarchical structure in it. And then we can also generate some posterior predictive data. Once we've got the posteriors on the thetas, we can generate, you know, data sets, posterior predictive distributions with the same number of trials. I think it was 200 earlier that I defined that we had in the actual simulated data. So you fit the model now, right? So as input for the data in list format, we have the number of trials, and we have the simulated, you know, responses. The model is fit as usual. This is taken from the BCOXI package. The M&M model, multinomial model, multinomial processing tree model using a multinomial likelihood, right? And then once you fit the model, this is all straightforward, right? We've done this before. We print out a summary of the posteriors of the parameters of interest, right? The parameters of interest could be A, T, F, and C. So you could look at those, right? That's what you would get here as these are latent variables, you know, in the model. These are theoretically posited probabilities, and so we're getting posteriors on those the um, from the model, right? Right. We can also derive once you have the posteriors. Remember that in Stan, what we are getting is a posterior distribution for each of the parameters. So we're actually getting, let's say 4,000 samples for each of these parameters as a stand-in for the posterior, right? So these are samples that we're getting. So one can use those ATFC vectors, the samples, we can use those to derive the probabilities of each of the possible categorical responses, right? Um, so what I mean is that I hope this is clear. What I'm trying to say is that you could take the posteriors. So for example, okay, you could take the posterior vector for A, for T and F and multiply those guys out to get the posterior probability of the posterior distribution of the correct responses. But I think that you will also be able to get that, or not I think, I know that you'll be able to get that from the Stan model as well. Right, so one important sanity check in model building is to check whether the model can, in principle, recover the true parameters. We know what they are because we define them. So the MCMC recover hist function again will show you that the vertical bars are the true parameters and the model is basically able to recover everything, right? Fairly accurately, not too bad. Now, as I said, we can also extract all the transform parameters posteriors. They're already there in Stan, so you don't have to do it by hand. So you just say that when you want to extract the theta posteriors, right? So what you get is the 5 posteriors for the theta directly from the Stan model. So you can use those and you can view those and you can see what you learn from the data plus the likelihood and the priors, okay? All right, so this is all, I think, fairly straightforward. So the cool thing here is that we started off by defining a latent sequence, of events that are theoretically posited, and we are able to derive the probabilities of each of those, paths in the tree from the model, and we're also able to figure out the posterior probabilities of each of the categorical responses. I think that's pretty cool. And in my talk on this, in an application talk that I will give, I will also show how this idea can be used in practical settings to gain significantly, or significant not in the frequentist sense, okay? So gain significantly more information about the processes that you're studying than just, by comparing average differences. Until now, we've been assuming that we don't have much variability between subjects and items, and for that reason we've been working with aggregated data, right? So we counted in whatever the number of trials was, 100 or 200. We have counts of the number of times each of the 5 categories was chosen or produced, and we don't actually have any information on what happened, for different items, because if there were multiple items and you have multiple participants, then different items will have, each of the items will have multiple data points associated with it, because multiple participants will see each of the items. And the items will differ one from the other, right? So you could have the word cat in one item. You could be showing a picture of a cat, which is relatively easy to identify and produce. But if you're showing the participants an umbrella and asking them to produce a much more complex word like that, then there will be a difference in the proportion of correct responses in those two kinds of items. So there will be between item variability. So what one can do is to take into account the complexity of the items. So this could mean word length differences or some other complexity metric that you could create, depending on the language and depending on what your theoretical interest is in. So, so what we're going to do is we're just going to, because we're just simulating data right now, we are going to assume that the complexity of the items varies, and we are going to have a numerical value that marks the complexity of the items, and we're going to scale it and center it, this complexity value. That means we're just going to generate simulated complexity differences between items by sampling from a standard normal distribution, mean zero, standard deviation 1. Okay, just for simplicity, that's how we will generate the different complexities of the items. All right, so the way to take into account the complexity in what is produced is in the following way, right? So suppose we want to assume that the parameter f is affected by the complexity of each trial, of each item, right? So in that case, we're going to use a regression approach, okay? So what we will do is, remember that f is a probability, right? So just like in logistic regression, okay? So in logistic regression, what we do is we model the probability variable which is bounded between 0 and 1 in log odd space, which is unbounded. And because it's unbounded, we can go ahead and use the standard linear modeling framework, right, with intercepts and slopes and stuff like that. So what we're going to do is we are going to convert the probability space to log odd space in order to model the complexity. So we're going to assume that there is some intercept and some slope that affects the log odds of the f parameter, right? So what was the f parameter? I actually forgot. So let's go back to the our interpretation here. The probability of retrieving the correct phonemes. Okay, so it could be affected by complexity. So what we're going to do now in the next stage is to model the probability of correctly retrieving the correct item as a function of complexity. So we have two parameters, the intercept and slope, and complexity is that continuous variable that we just defined that that indexes complexity. A positive value means more complex, negative value means less complex, and the zero value means average complexity across the items, right? So our expectation is going to be that the greater the complexity, the lower the log odds, right, of correct item being retrieved. So this slope parameter would have to be set to a negative value, right, in our simulation, right? So we're going to model the f parameter in log odd space and then convert back to probability space, right? So as you probably know, in logistic regression, in R, there are two important functions, the q-logis function and the p-logis function. The q-logis function converts probabilities to log odd space, and the p-logis functions does the inverse of that, right? So we can, once we have all the estimates in log odd space, we can always convert back to probability space to get the probability values that correspond to the f parameter, right? So this is just to remind you what logistic regression is like. So we got log odds for some probability, and this index j is indexing the different items now. Okay, so every item will have a different complexity value, and so what will happen is that the log odds by item will differ, right? So then we can convert back to probability for each item, okay, by taking the solving for p basically in this equation, right? So if you treat this right hand side of this equation as mu sub j because it's indexed by item, then we can back transform to probability space. That's what the p-logis function does, by the way. It gives you back the probability once you plug in the logouts for a particular complexity level, right? So what we'll be doing is we'll be plugging in for a particular item j equal to 1, say, right? So the first item, we plug in the complexity value of item 1, we compute this entire additive term, that becomes our mu sub 1, right? And then we convert it back to probability space to get the probability of correct retrieval for that particular item, right? So this is all standard logistic regression. Nothing new here. It's just the standard logistic regression approach, right? In the generalized linear model. So we're going to generate some data now. Let's say we generate 50 observations. Set up the alpha underscore f parameter. So that's the one in the log odd space for f. The intercept parameter at 0.3. The slope parameter is minus 0.3, minus because increasing the complexity will reduce the log odds, right? And so then once you do that, you can actually compute for all the complexity values. So this is a vector of complexities generated from the standard normal, and these are fixed values, alpha and beta f, and so you get f prime, which is in log odd space. So these would be the numbers that you see in log odd space, and they're not bounded between 0 and 1 anymore because they're log odds, right? And so you can use the p-logis function to back transform that vector of log odds for the different items back to probability space. So now you have numbers that are constrained between 0 and 1, right? That's the beauty of the logistic regression approach. So this is how we will proceed now. We are not going to mess with A, T, and C parameters, right? We're just going to mess with the F parameter, have it vary by item, okay? So if you remember, like when we compute all the different theta probabilities, you know, the 5 theta probabilities, F is usually involved in those, right? And F is now a vector, right? This is a vector now, and therefore we are gonna have to have vector representations, you know, because there'll be multiple items, so we're gonna have multiple thetas for different items, okay? So the only exception here will be the non-response theta vector, which actually doesn't even depend on f, right? So it's just a single a true value that we use, I think, if I remember correctly. And so we're just going to create a vector out of the, you know, the result of this function, right, which only depends on a true. We're just going to repeat those values across the items. So that if we have, let's say, 50 items that we are looking at, that's what the number of observations was, I think. Yeah, 50 items. Therefore, we're going to repeat the same probability 50 times, right? So we are not assuming, we are assuming that the between item variability non-response is the same. Of course, you could change that assumption, right? But just for simplicity, we're only messing with the f parameter. All right, so, and then we get to, let's see, where are we? Yeah, so the rest of the thetas will all be vectors anyway, because we'll be getting we'll be plugging in, f true will be involved, and f true is a vector, right? So this will all end up becoming a vector. So we will have vectors of thetas now. So that's why we have to create a matrix representation for the thetas by item, okay? So that's why this is no longer a single vector, but it's a matrix now with 5 columns. Why 5 columns? Because each column will represent the different theta values, the 5 different theta values, and the number of rows will be the number of items. So if you look at the dimensions, 50 rows, that's the 50 number of items, and 5 columns representing the 5 thetas, right? So this is what it looks like if I look at the matrix now. Notice that the non-responses are always going to be completely invariant because they don't depend on items. All the others are slightly different, as you notice, and that's because F is involved in those. And so for every row, that means every item, there'll be a different probability, right? So I'll store all this now in a data frame, okay? So we got 50 items. So items is 1 to number of observations. Complexity is the vector we created from the standard normal. And now we have the answer, so the response. Taking as using the categorical variable, because we are no longer modeling aggregates, we are modeling at the trial level now. For every single trial there'll be one choice that will be made for every item. So for we have 50 items, therefore we are carrying out 50 experiments essentially, and then we are plugging in the theta matrix into the rcat function to produce a particular response for every particular item. Okay, so what this looks like is the following. Okay, once I run this command, what I will get as a result is 50 rows and 3 columns. So the items 1 to 50, complexity is randomly generated from standard normal, and in the w-ans we'll get one number which tells us which response was given. So this is the correct response, 1 would be the non-response, etc. Okay, all right. So this is all randomly generated. Of course, if I ran it again, I would get different numbers unless I set a seed or something like that. Okay, so now the model which is saved in your bcogSci library, right? The mpt cat for the categorical likelihood will look like this. Okay, as input, of course, we're going to give it a list of containing the number of observations, and we are also going to give it the vector of responses, which are ranging from 1 to 5, and it's an array that has 50 elements in it. Okay, so that's what that statement is. The parameters do not change. Okay, they're all as before. The transform parameters now look like this. So notice first of all that theta is now an array containing n obs, so 50 elements, and each element contains a simplex vector, because each of the 50 items is going to contain the vector of probabilities for for that particular item, right? So that's why we have a statement which you've never seen before so far, which is we are defining an array of 50 elements, and each element contains a simplex. Why simplex? Because we want the probabilities for each item to sum up to 1. Okay. So now, because we have 50 observations, so 50 items, we're going to go through the entire, we're going to go row by row now. For the 50 items, we're going to go one by one and compute for every single item the different thetas. So the theta 1, theta 2, theta 3, theta 4, and theta 5. We'll be saving this in this object here that we defined, in this array, right? This array will contain the probabilities that will be computed using those same equations that we had, and nothing has changed there. Okay, so it's just the same as before. Right, so that's my transform parameters. Nothing new there, except that we are using a for loop to cycle through the 50 items and to create the vector of thetas, the 5 thetas, right? So now the model again is pretty straightforward, right? So we've got the 4 priors for the ATFC parameters. And again, we're going to write a for loop that goes through the 50 items and defines for each item a categorical likelihood that is modeling the response for the nth item, right, as a function of the nth item's vector of probabilities, right? So the 5 elements in each cell of the array that contains 50 elements. Okay, so that's how we are modeling now the responses on a non-aggregated level, right? So by item now. And so in the generated quantities, we're doing exactly the same thing, nothing different except that we're using a random number generator. And here what's going on is that these thetas for each of the items will be the posteriors after having seen the data. Okay, so these are going to be the generated data, the posterior predictive data will be stored in this array, and it will contain numbers ranging from 1 to 5. That's why they're integers, and so there'll be 50 of those. Okay, so that's it. Okay, so that's the discussion about adding by item variability into the model. Okay, so the next topic that I will cover is a hierarchical version of the multinomial processing tree model. This is a bit more involved, so tighten your seatbelts, maybe go and get a coffee first, and then we are going to get back to this. Okay, so now let's look at the hierarchical version of the multinomial processing tree model. In this setup, what we're going to do is we're going to add varying intercepts for subjects, right? So if you remember in the standard linear mixed modeling setting, if you're using BRMS, for example, right, you would write something like BRM, then you have some dependent measure as a function of intercept plus some predictor, right, that would be involved in affecting the dependent variable, and then you might add something like 1 plus subject, right, as your varying intercepts term, and then of course the rest of the specifications come in Elmer also. It's the same kind of setup, right? It's all the same as what I've written above. So this everyone is familiar with, I think. So the underlying mathematical model though is assuming some likelihood for y, right? If I were to write out this model or this model, right, same thing, as a mathematical model, I would say that there would be some likelihood. Let's say, I mean, if it's response times or reading times or something, I would use the log normal likelihood, and then I would assume that there is some intercept, and then there would be some subject adjustment, right? So if subjects are indexed by the subscript I, there would be an adjustment to the intercept, which I'll just call 0, right? U sub 0 refers to the intercept adjustment for each of the ith subjects, right? And then there would be, oh gosh, it's over-engineered nonsense by Apple. So then I would get a slope with some x value and then some standard deviation term. And then so the interesting thing now is that, of course, there would be priors defined for the parameters, but the interesting thing is this guy here, right? So in the linear mixed model, what we do is we would define, actually we don't use the subscript here. We would define this statement that this by subject adjustments to the intercept, to the overall intercept, are coming from a normal distribution with some standard deviation tau, which I'll call tau u0 or something, right? So what's important to notice is that we add a between subject variability parameter in the model when we introduce this kind of hierarchical structure, right? We are assuming between subject variability now. Now, one very interesting piece of syntax that Andrew Gellman introduced As far as I know, it was he who did it in the book, you know, the Gelman and Hill book, 2006 or 7 or something like that, Cambridge University Press. In this textbook, he introduced when writing out code, you know, in WinBugs. Was it WinBugs? Actually, I don't remember, but now, in any case, the way he wrote the model was like this. He would assume that the data are coming from some likelihood, let's say log normal, with some intercept. That's only just one, you know, overall number, so there's no subscripts there. So he would assume that there are n rows in the data frame, in the data, okay? N indexes the row. And so for the subject adjustment to the intercept, what he would write is something like this, okay? So subject, right? So this syntax, you can think of this as a, well, no, it is actually a function, right? So what this is saying is, what Gelman is saying here is that the subject ID in the nth row is the value of this I variable here, okay? That's what this syntax does. So this is the syntax that we are also going to use in the book as well as in today's lecture. So just keep that in mind, okay? So that's the background I wanted to cover before getting into the lecture. So let's go back here, right? So the hierarchical model. So now we're going to assume some between subject variability, and in particular, we'll assume that there's some variability in the amount of motivation that participants might have, and that would affect the A parameter, right? So the very first decision point is whether to give a response or not. So if they are under motivated, they might not want to give a response. So the A parameter is going to vary by participant, okay? Just by assumption, just for simplicity here, okay? So we're going to assume that now we have 20 items and 30 subjects. Therefore, if we assume that every subject sees every item, and I'm assuming here in the same order, right? So then we have 600 observations, so number of items times number of subjects, and so we can create a vector for subject IDs such that each of the 30 subjects is seeing 20 instances, 20 items, right? So therefore we are using the rep function in R to produce 1 to 30, but each of those numbers going from 1 to 30 is repeated 20 times, right? And then we've got the item IDs, so we're going to go from 1 to 20, but we're going to keep cycling the numbers 1 to 20 for as many subjects as we have. That's what this syntax does. So it produces a sequence like 1 to 20, 1 to 20, 1 to 20, 30 times, right? Whereas this sequence, the rep sequence for subject, is going to produce the number 1 for subject 1 20 times, then the number 2 for subject 2 20 times, and so on, right? That's what happened. And then we produce the complexity values just randomly generated, of course, from a standard normal. Because there are 20 items, we are assuming 20 randomly generated values, and we will then again put those in for each of the 20 items for each of the 30 subjects. So that's what this syntax does. So we're going to save all this as the data frame, or tibble rather, xsim, so simulated experiment, okay? So we got a subject column, item column, and we go to the complexity column. That's the complexity column there, okay? So that's what the data frame looks like. So now, because we have between subject variability in the A parameter, we're going to assume, for simulating data, we're going to assume that we have a tau parameter for the adjustment by subjects to the A parameter. That's why it's called tau UA. We're just choosing some number in log odd space like 1.1, okay? If you want to know what that 1.1 is in probability space, you can of course compute that, but it doesn't make any sense here because we're doing all our computations in log odds space, and this tau parameter is actually referring to the tau, to the log odds space variability here, right? So it wouldn't make sense to back transform this to probability. Okay, so people often ask me that question, so I just thought I'd mention it. All right, so now what we're going to do with this tau UA in log odds space is we're going to generate for the 30 subjects, we're going to produce an intercept adjustment for each of the subjects from a normal distribution, right? Remember, because in the model we are assuming that the data are coming from a normal distribution with mean 0 and some between subject variability. That's what this statement is saying, right? That we are sampling from not a standard normal, sorry, from a normal distribution with mean 0 and tau UA as the standard deviation. Obviously not a standard normal, right? Standard normal would assume tau for, UA equal to 1, obviously. So sorry, I misspoke there. So anyway, now we've produced our intercept adjustments. This is actually a very important line of syntax. This is how we also generate simulated data when doing power analysis in the frequentist setting for computing power in complex repeated measures designs. We can't do that, do power calculations using analytical methods anymore. So we simulate data. This is how we simulate the data. We basically generate intercept and slope adjustments like this. Okay, so that's a different topic, but I just wanted to mention this is a very important tool for simulating data. So now we have 30 data points in this intercept adjustments. So these are the different adjustments in log odds space. Okay, don't forget that. So we now proceed as follows. Working still in log odds space, for the A parameter, we're going to have an intercept that we're going to adjust by subject. So here comes the Gelman syntax, okay, the Gelman and Hill syntax. So for in the nth row of the data frame, we can look up the subject ID, right? So for example, if you look here, the first row of the data frame contains some subject ID. That's ID 1. The second row contains subject ID 1 as well. So if I know the row of the data frame, subj and the row ID tells me what the subject ID is. That's what that syntax is doing, okay? So I'm going to put in the relevant, for the nth row in the data frame, I'm going to put in the relevant intercept adjustment by subject. And once I've computed that, I back transform to probability space to get my A parameter values for each of the 30 subjects in probability space. Okay, so this is my A true, the overall probability we had always assumed, for for responding. So A true was the probability of responding, and we can convert that A parameter to log odds space using the QLogis function. So that's what I did here. That gives us the alpha parameter in log odds space, this alpha parameter in log odds space. And then what we do is that we carry out the linear additive term, So for the log odds space alpha value, we're going to add the log odds space intercept adjustment, or the adjustment to that alpha in log odds space. So we get, for each subject, we get an A prime in log odds space, which we can back transform using the plogis function. So what we get is a vector of 30 values here. Sorry, not 30 values. We're going to get a vector here that gives us the A probability values, okay, in the entire data frame, because we have gone through the entire data frame, right? So we've gone through the entire data frame to produce these A values, because they're going to vary by subject, right? So what we get is, notice in this output, the vector that I've created here, this contains, because I have the first subject has 20 instances repeated. Therefore, the A value for that subject will be the same, right? If I were to keep looking down, at the entire vector here, there's 600 elements. Why 600? Because 20 times 30, 30 subjects and 20 items, right? So 600. And so the first 30 elements in this vector will be 0.481 because they represent the alpha for subject 1. Then the 41st element onwards for the next 20 elements is going to contain the second subject's data. So the first 20 elements will contain the first subject's A parameter value. The second 20 will contain the second subject's parameter value, and so on, right? That's what we get here. So we are computing alpha f just like before as a function of item complexity. So that's just the same thing I did earlier, just repeating that now. And we get an f true vector. We're going to get a vector here because we've got complexity values, 20 complexity values here, right, for the different items. Okay, so now it's going to start to get a little bit hairy, but it's still not too bad. Okay, so what we now got is the same parameters for T and C. Okay, those are not varying at all by item or subject. And then these are the same functions that we computed earlier. And just repeating the old functions, okay? So now we can compute the probabilities for each of the 5 possible responses and save them as a vector, a matrix, as a matrix containing 600 rows and 5 columns, right? Because 600 rows, because we have 20 times 30 rows and we have 5 columns now. Okay, so all these calculations are just like before. One thing to notice here is that earlier what I had in the code was that we repeated this result multiple times, but now A through H is actually a vector, therefore we don't need to repeat it anymore, right? So it's going to be this is going to be a vector as well now, right? So there'll be values for 600 different elements in the row. So one thing you should do when you're working through these notes after listening to this lecture is to rerun the code yourself line by line, so code chunk by code chunk, and then examine the output so that you understand what theta sub h actually looks like and why it looks like that. Okay, by just passively listening to me talk, it may not be 100% clear, okay, because I'm going fast, right? I'm trying to finish this lecture in finite time. So, but you will need to go back and revisit the code and rerun it yourself. Otherwise, you will not be able to internalize what's going on, okay? All right, so now what we do is we just add to the old data frame that we had, which only had subject, item, and complexity. We are adding one more column, which is the response by randomly generating categorical data. 600 observations, right, is what we have. And the theta sub h vector, sorry, not vector, but matrix, is actually giving me the relevant probabilities that I need to produce those 600 randomly generated values, which will range from 1 to 5. Okay, so that's the setup now. That's my data, okay, simulated data. And now earlier we had used the logistic function in a regression, but we are now going to in the stand code, you will see that I've used their built-in logistic regression function. Okay, so I'll show you what I'm talking about. Let's look at the mathematical statement of the model. For the alpha A and alpha F parameters, we just choose some reasonable priors here. This we've just chosen from experience, with the problem. For beta also, it's some reasonable value. Here also we're using beta 2 just like before. And here's the new parameter tau u, which is a truncated normal. That's what that plus means, right? Truncated normal, which is the standard normal here. So we just chose a reasonable prior. In log-odd space, this makes sense, okay? We discussed that in the textbook in the logistic regression chapter. And then we are defining how the subject adjustments happen, right? That's just the statement of the standard linear mixed model. And then here we are using the inverse logic to compute the f values in probability space, just like I did before, but now I've written it in directly here because here's the model in log-odd space, and then go back into probability space here. And then all the other probabilities you've seen before, nothing new here, nothing to see here, nothing special. The only thing that's new now is that we are now fitting a categorical model with theta sub n. N is indexing the 600 rows, you know, of the data frame, okay? So that's why there's a subscript n here everywhere, okay? You see that? There's a subscript n everywhere because we are modeling everything row by row now, okay? Very important idea. So the model looks like this in STAN. We got the number of observations, which is 600. All this goes into the data object, right? And then we've got the responses, which is a number between 1 and 5, 600 of those. And then we've got the complexity, also 600 times. Number of subjects is ranging from, is 30, but starting with 1. So we set it up like that, right? And then we've got the subject column, right, contains the numbers 1 to 30, and it has a total of 600 observations. That's what is specified here, okay? That's what this statement is saying. All right, so the parameters you've seen before. There's nothing special going on here except this one. This is the new parameter, right? This parameter is the between subject variability in the A parameter, okay, in log-odd space, okay? And then we go to the transform parameters. Here things get interesting because again, this you've seen before. This is the theta parameters specification, because it's going to be an array containing 600 elements, and each element will contain 5 values, you know, simplex values. Okay, that's what this statement says. Then we are going to walk through the 600 observations. So that's why we have got a for loop going from 1 to number of observations, which is 600, right? So what we're going to do is, first of all, we are going to compute in probability space. We are going to take the alpha parameter. We're going to take the subject adjustments. Here comes the Gelman syntax, okay? This is telling you what the subject ID is in this vector, okay? In the nth row of the data frame. And so we are using the inverse logic, which is the p-logis function, okay, to get back the probability space. Again, we're using the equivalent of the p-logis function here to compute the f, right? So all this is in log-odd space. This is in log-odd space, and we're going right back to probability space right inside the STAN model now, okay? And then the rest is all straightforward, nothing new there, all as before. And then the model statement is also very straightforward. You've got the beta priors for T and C. For alpha, A, alpha F, beta F, we have those priors. And this is the specification for how the intercept adjustments are assumed to be the A adjustments to the A parameter, you know, how they are being, what the between subject variability will be, and what those values will be. They're assumed to be coming from a normal distribution. That's the normal log PDF function, right? So we are assuming that the U sub A is coming from a normal distribution with mean 0 and between subject variability in log-odd space at tau UA, okay? So all these statements are clear. So these are all in log, these are all of these parameters are in log-odd space, okay? And the next one is also in log-odd space. This is the prior on the tau parameter, and this is assumed to be a standard normal, just like I showed you earlier in the mathematical model. This minus normal log complement of the CDF, what this is doing is it's just truncating the normal at 0. So graphically what's happening is we are specifying, let's go back to my little, right? So what we wanted is for tau u, what is it, a or something, right? So we have normal 0. Oh, sorry, what am I saying here? Yeah, right, that's the prior, right? That's correct. So that's the standard normal, but we don't want a standard normal here because we don't want the tau parameter to be positive or negative. Like standard deviations can't be negative, right? These are negative values. So we're going to truncate this whole thing, right? And so that's why we write in the text, when we write the mathematical model, we write n subscript plus to represent the fact that we are only considering this part of the standard normal distribution. And so in Stan syntax, this is discussed in the textbook, but so I won't really discuss this too much, but basically this is just Stan syntax for truncating the normal distribution and making sure that the area under the curve in the truncated normal distribution still sums up to 1. Okay, so it's a proper PDF, probability density function. All right, so then what we do is we define the actual likelihood function just like before, and now what we are saying is that for the nth element in the data frame, so there are 600 elements in the data frame, for the nth element, the generated the value that is observed in our simulated data is coming from a categorical distribution with theta that is the theta that is in the nth row, right? That we had specified. Okay, so that's the statement of the likelihood function, and then the same thing happens when you're producing posterior predictive data, just like before. So this, we are just literally copying over the syntax, except that instead of using categorical log probability mass function, we're using categorical random number generator to generate new data, right, based on the posteriors of this of these parameters. Okay, so one side note here is that one could have made this model much more efficient with some non-centered parameterization, which is discussed in the textbook again, and also of course in the Stan manual, but we won't do that here because it just complicates the whole story even further. So let's not do that. Okay, so now we're going to set up the data for actually running the model, right? So we got the number of observations, WANS, so the answers, so the response is subject, and complexity. Yeah, we don't need the item variable here. Okay, right. So then we get to the MPT underscore H model, which is also available in BCOG side. So that's the model that we save, and we plug it into Stan with the list, representation, the list representation of the data. Okay, and once you fit the model, you can look at the various parameters in the model, and you can see the posteriors here and draw your inferences from that. Okay, so you should read all this later on to see what you could conclude from this model. I mean, I don't want to discuss this because it's just simulated data anyway, but what I do want to talk about is if you want to derive, for example, the value of f for a particular item, if you want to know what the effect is of 1 unit increase in complexity, okay, on 1 unit increase in complexity on the f parameter, what you would do is the following, right? So remember we created an f prime parameter which was some alpha plus beta times complexity in, this is all in log odd space, right? So what we would do is, if the question is, right, if the question is what is the change in the f parameter. What is the predicted change, I guess I should say, by the model. In the f parameter, when we increase complexity by 1 unit. That could be a useful question to ask, right? So it would be easy to do this, right? So how do we do that? We have this f prime calculation. We know what this is. We know what this is, and if this we have an estimate of, okay, from the stand model, right? We even have like thousands of samples for this, for the posterior distribution of this parameter, right? So what we can do is we can just use the plogis function in R and plug in the vector of posterior samples for this, and this would give me back the alpha in probability space. I shouldn't call it alpha, let's call it, I don't know, let's call it the intercept, okay? The intercept in alpha in probability space. Well, actually it is alpha in probability space. So okay, so let me just go back and not be stupid about this. So right, so alpha in probability space, and then what I could then do is I could use the plogis function again and compute alpha plus betas, because what I want to know is what's the difference between complexity 0 and complexity 1, right? Complexity 0 is this one here. Complexity 1 is this one here. So now I can get alpha plus beta in probability space, right? I get that. And now if I just subtract from this term or this vector, I'm going to get the posterior distribution of the change in probability. So I'm actually going to get a posterior distribution that represents the change in probability when we have 1 unit increase in complexity. If these were point values, I would get a single point value that tells me the change in complexity, right? So that's a very useful calculation to do, and it requires knowledge of the way logistic regression works, right? So this is what I've done here, or what we've done here. We're going to compute first we're going to compute alpha plus 0 times beta in probability space. Then we're going to compute alpha plus 1 times beta in probability space and take the difference between them, right? So this is all this complex code here. See that f0, f1 is being computed, and f1 minus f0 is what I just did. This is the difference between these two. So in the lecture notes, this term is called f1 and this term is called f0. Okay, so I'm just computing f1 minus f0, and that gives me a probability distribution actually, right? That's the difference f here in probability space, right? And you can look at the entire 5-number or 4-number summary of that, right? So now we have a decrease of 5% with a 95% credible interval going from so it's minus 5% and going from minus 10% to minus 0.6%, right? So that's basically, it's giving you a lot more information than a point value, right? That's the beauty of the whole Bayesian paradigm, that you can quantify your uncertainty about whatever quantity you're interested in, okay? All right, so that's just one demonstration of how one could use, the posteriors. These are all, we have posteriors for everything in the model. So we can manipulate those and figure out whatever, probability quantity or we want to understand, including its uncertainty, because we'll have a posterior distribution on that, okay? So we could also like look to see if the parameters in the model recovered the true values that we set up, just like earlier, and you see that the model is doing pretty okay, right? And another thing you can do is this is the cool part now, okay, with hierarchical models. You got individual subjects posteriors now, the shrunken estimates plus the alpha, okay? So in the hierarchical model, you could plot the, the posterior predicted values with the 95% credible intervals against the observed data. Okay, that's the uh, blue colored histograms are the observed data, and these are the posterior predictive values. So you can see that the model on the aggregate is producing pretty reasonable, data, but you can go even further, and this is where the real interesting action begins. For each of the 30 subjects, right? So you have 30 subjects. For each of the subjects, you can get individual level predictions, posterior predictions for each of the 5 categories. So you'll notice if you look carefully at these plots, for example, here and here, you'll see that subject 1 and subject 6 are very different in their value 1, which is the giving a non-response, right? So you'll see this individual level variability, which could be of great interest actually if you're studying individual differences, or if you want to understand how people vary in their behavior as a function of perhaps some theoretical construct, right? All this could be studied now. So one interesting thing to notice is that if you were to produce this kind of plot with the non-hierarchical model, what we would get is something very interesting, right? It would look of course the non-hierarchical model would also give us reasonable posterior predictive distributions, but if we tried to plot the individual level differences in the non-hierarchical model, obviously, right, this is not surprising, but obviously for every single subject the predictions are exactly the same. There's no difference because the model doesn't assume any between subject variability, obviously, right? It's not surprising, but I just want to point out the huge advantage, of going from non-hierarchical to hierarchical models. Okay, so that's about it for this topic, and I just wanted to point out that there are several papers that have come out from my lab led by Dario Papa, whose webpage is linked here. And there are 3 papers, 2 or 3 papers. I guess I've just listed 2 here. So there's 2 papers here in which multinomial processing trees have been heavily used to derive theoretical conclusions that advance our understanding of the topic that we were studying. Okay, and this is the topic that I will cover in the practical applications talk relating to multinomial processing trees. So I hope that this lecture, which I think is a little bit long, so you should watch it in I hope you watched it in breaks, with breaks. This lecture gives you a good understanding of how multinomial processing tree models are set up, how they can be made hierarchical, and how you can derive important conclusions, from the parameters that you get, the posterior distributions that you get from these models.